Hello viewers, welcome once again. We are still under logic, cried Almighty God's algebra. In our last tutorial, we treated law of distribution by conjunctive statement. Today we are going to treat law of distribution by disjunctive statement. Let us start. Law of distribution. P or bracket not P and Q is equal to bracket P or not P and bracket P or Q. This is a typical example of law of distribution by disjunctive statement. Because of this or connective that connects the first disjunct P and second disjunct bracket not P and the Q that makes the statement disjunctive statement. That's why it is called law of distribution by disjunctive statement. You see that this side is equal to this side, in the sense that this P or is distributed over not P and the Q. So let us prove the statement that it is true that it is law of distribution by disjunctive statement. Prove. Suppose P or bracket not P and Q is equal to bracket P or not P and bracket P or Q. We assume that the statement is true and it's a hypothesis. We are going to prove it that it is true that P or bracket not P or not P and Q is equal to bracket P or not P and bracket P or Q. If you look at this equation, you will find out that whenever the left hand side of the equation is true, also the right hand side of the equation is also true. In the same vein, whenever the right hand side of the equation is false, also the left hand side of the equation is also false. So you say that they are equal. So it is true they are equal if it is true that whenever the left hand side of the equation is true, also the right hand side of the equation must also be true. If right hand side of the equation is false, also left hand side of the equation also must also be false. We say that it is equal, they are equal. So we're going to prove it. So this is true, also this also must also be true. If and only if P or brackets not P and Q, if and only if bracket P or not P and bracket P or Q is tautology being justified by logical equivalence. Now, we have now transformed this equation to biconditional statement and is tautology. So it is true logical equivalence that we transform this statement to biconditional statement and its tautology. Why is it tautology? That means it is true that this statement is tautology, which equivalent to this equation. Because if this equation is true, we assume that it is true. And if it is true, this also is true. Because whenever the left equivalent is true, also the right equivalent must also be true. In the same vein, whenever the right equivalent is false, also the left equivalent must also be false. So if you value this statement, there's no possibility of falsity, always truth. We say that the statement is tautology, being justified by logical equivalent. Also, if this is true, also this also must also be true. If and only if P or bracket not P and Q implies bracket P or not P and bracket P or Q is tautology, being justified by logical implication. Now you see that this statement, this biconditional statement, has now been transformed to conditional statement and it still maintains tautology. In the sense that whenever the antecedent is true, also the consequent must also be true. So if you look at this statement, there's no possibility of falsity, always truth. We say that the statement is tautology. So being justified by logical implication. It's through logical implication that we transform this statement, this biconditional statement, to conditional statement, and it still maintain tautology. It is still truth, which is equivalent value to the this biconditional statement. So if this is true, also this also must also be true. If and only if P or bracket not P and Q is logical implication of bracket P or not P and bracket P or Q. Now we have now derived that P or bracket not P and Q, that is antecedent, is logical implication of the consequent bracket P or not P and bracket P or Q. So by the principle of logical implication, we derive that this is a logical implication of the consequence. I mean, the antecedent is logical implication of consequence. In the sense that the antecedent is a proper implication of the consequence. That means it is a subset of the consequence. So it is true that it exists. So that's why it's being derived as logical implication of the consequence. So if this is true, also this also must also be true. So if and only if P and bracket not P, not only if P or bracket not P and Q is equal to P or bracket not P and Q. So it is true that logical implication is equal to itself. That means whenever the right hand side of the left hand side of logical implication is true, also the right hand side of logical implication is also true. In the same vein, whenever the right hand side of logical implication is false, also the left logical implication is also false. You say they are equal. So it is true that logical implication is equal to itself. Because it is true. They have the same value. So being justified by the sameness, by identity. That means the sameness. By identity. So if and only if P or brackets not P and Q is equal to bracket not P and Q is not P. We have seen that this statement, this disjunctive statement, P or bracket not P and Q, has now been transformed to conditional statement through first edge case law. So you see that this statement is equivalent to this statement. In the sense that, see, this is P or Q is also P or Q. So it still maintain, it is still law. It's not yet grace, it is law. So being justified by first edge case law. If and only if P or brackets not P and Q is equal to not P upon not P and bracket Q upon not P. See that it's still equal. What we did here is that we distributed this implication not P between not P and the Q. That's why I have not P upon not P and Q upon not P. And it's still logical, is still equal to the other side of the equation. So be justified by distribution of implication. It is through distribution of implication that we state that implication between not P and the Q. Being justified by distribution of implication. If and only if not P or bracket not P and Q is equal to. Now we are going to revise these statements, these question statements, to disjunctive statements. Reason is because of this not P is being generated from the disjunctive statement. So whenever I want to revise it, it's going to be in disjunctive statement. Sorry, before then, you are going to have not P and Q. Not P and Q. Okay, sorry. We are still in order. So you're going to reverse these statements, these two statements, this conditional statement, to disjunctive statement, because this not P is being derived from the disjunctive statement. So whenever I want to revise it, it's going to be in disjunctive statement. That means we're going to have bracket P or not P and bracket P or Q. So it's through first education law that we transform these question statements to disjunctive statements. So it's been justified by first education law. First education law. We see that we have now proved our hypothesis. We have now proved this our hypothesis that P or bracket not P and Q is equal to bracket P or not P and bracket P or Q, which is the same as P or bracket not P and Q is equal to bracket P or not P and bracket P or Q. So we have proved the hypothesis. That was not shown. We have now proved it that it is true. So we then conclude. We say thus P or bracket not P and Q is equal to bracket P or not P and bracket P or Q. So having proved the hypothesis, we are going to prove the converse. So by the principle of essentiality, we then establish that P or bracket not P and Q is equal to bracket P or not P and bracket P or Q is law of distribution by disjunctive statement. So let's prove the converse. Conversely, bracket P or not P and bracket P or Q is equal to P or bracket not P and Q. So we see the converse of this statement. You see that here P or bracket not P and Q is at the left hand side of the equation here. Now it is now at the right hand side of the equation here. Bracket P or not P and bracket P or Q is at the right hand side of the equation here. Here is now at left hand side of the equation here. So you say that it is converse. Let's prove this converse. We assume that it is true. The statement is true. So, and if it is true, if I assume it is true, it's because our hypothesis. So we're going to prove that it is true. So suppose bracket P or not P and bracket P or Q is equal to P or bracket not P and Q. So we assume that statement is true. That's why we say that bracket P or not P and bracket P or Q is equal to P or bracket not P and the Q. We assume that it is true. We say that whenever the left hand side equation is true, also the right hand side equation must also be true. In the same vein, whenever the right hand side equation is false, also the left hand side equation must also be false. You say that it is equivalent. That means it is equal. The both sides of the equation they are equal. So it is true that they are equal if they have the same value. Left hand side of the equation have the same value with right hand side of the equation. So we continue to this side. We say that let us transform this statement to biconditional statement. We are going to say if and only if P bracket P or not P and bracket P or Q, if and only if P or bracket not P and Q is tautology, being justified by logical equivalence. Now, this statement, this equation has now been transformed to biconditional statement in the sense that, and is tautology, in the sense that whenever the left equivalent is true, also the right equivalent must also be true. Whenever the right equivalent is false, also the left equivalent must also be false. So this statement, if you evaluate it, that's not particularly false, it is always true. You say it is tautology, which have the same value, the same truth value with this equation, and is being transformed to biconditional statement through logical equivalence. They continue. Say if and only if bracket P or not P and bracket P or Q implies P or bracket not P and Q is tautology, being justified by logical implication. You see that this statement, this biconditional statement has now been transformed to conditional statement, and it still preserves tautology. In the sense that whenever the antecedent is true, also the consequence must also be true. So if you write this statement, that's not negative positive, always to say that it is tautology, which have the same value with this biconditional statement, truth. So, and this statement is being transformed to conditional statement through logical implication. That's why it's being justified by logical implication. So, if and only if bracket P or not P and bracket P or Q is logical implication of P or bracket not P and Q. You see that this statement, that is this conditional statement, is tautology. And this tautology we then derive that bracket P or not P and bracket P or Q is logical implication of P or bracket not P and the Q, I mean the consequence. Now you see that by the principle of logical implication, we derive that this statement is a logical implication of this statement. That means the antecedent is logical implication of the consequence. In the sense that the antecedent is a proper implication of the consequence. So if that is the case, we say that the antecedent exists. It is true that antecedent exists because it's a proper implication of the consequence. So we then say that the antecedent is logical implication of the consequence by principle of logical implication. So we continue. Say if and only if bracket P or not P and bracket P or Q is equal to bracket P or not P and bracket P or Q. So if this is true, also this also must also be true. In the sense that the logical implication is equal to itself. So it is true that logical implication is equal to itself, because whenever the left hand side of logical implication is true, also the right hand side of logical implication must also be true. In the same vein, whenever the right hand side of logical implication is false, also the left hand side of logical implication is also false. We say that they are equal. So it is true that they are equal, being justified by identity. That means the sameness. They are the same. Being justified by identity. We continue to this side. If and only if bracket P or not P and bracket P or Q is equal to not P upon not P and Q upon not P. We see that we have transformed these statements, this conditional statement, we transform it, this conditional statement, we transform it to conditional statements. That's why we have not P implies not P and not P implies Q. That means not P upon not P and Q upon not P. So, being justified by first edge case law is through first edge case law that we transform this statement, this disjunctive statement, these two disjunctive statements to that conditional statement. So, being justified by first edge case law. If and only if bracket P or not P and bracket P or Q is equal to not P and Q upon not P. So we see that this statement is equivalent to this statement, is their logical equivalent, in the sense that this not P is distributed between not P and the Q. So it's distributed between not P and the Q by the sphere of implication. So you have the sphere of implication by law and the sphere of implication by grace. So this one is the sphere of implication by law. That's why it's equivalent to this. So this is equivalent to this. So we should relate this with this. So it's being justified by the sphere of implication. Being justified by distribution of implication. If and only if bracket P or not P and bracket P or Q is equal to. Now, we are going to transform this conditional statement to disjunctive statement, in the sense that this not P, this implication is being derived by disjunctive statements. We derive it here and here. So we are going to revise it to disjunctive statement. That is going to be P or bracket not P and the Q. So, and it's being revised to disjunctive statement through first case law. It's through first case law that we transform it to revise it to disjunctive statement, and that is still law. So being justified by first case law. You see that I've now proved the hypothesis. I've now proved the hypothesis that bracket P or not P and bracket P or Q is equal to P or bracket not P and the Q. We then conclude. We say thus bracket P or not P and bracket P or Q is equal to P or bracket not P and the Q. Having proved the converse, so by the principle of externality, we then establish that P or bracket not P or Q, bracket P or bracket P or bracket P or bracket not P and Q is equal to bracket P or not P and bracket P or Q is law of distribution by disjunctive statement. We then conclude. Therefore, P or bracket not P and Q is equal to bracket P or not P and bracket P or Q is law of distribution by disjunctive statement. Having proved the converse, we then established by the principle of externality that P or bracket not P and Q is equal to bracket P or not P and bracket P or Q is law of distribution by disjunctive statement. So at this juncture, we shall draw our curtain. Thank you, viewers.